sketch in about maybe 20 minutes, okay? So, problem set 5, I did just kind of go around and do a look. If you don't have units or work, no credit, okay? And it's not because I know you can divide in your calculator, and you can multiply, I know you can do math, but again, it's the skill of incorporating units, because we're not doing math, we're doing chemistry, and everything is a measurement at this point, or everything is regarding some sort of special characteristic like frequency. So we need to make sure we recognize that. So when I switch this up, I'm expecting that your units are clearly denoted on your work, okay? So S block incorporates both what two groups of the periodic table? Alkali and alkaline earth. D block incorporates all of transition metals. P block incorporates basically all the nonmetals, right? Do you see that 1s over there? It actually belongs here. We'll talk about that shortly. And then F block are all the inner transition metals. All right, so halt on this for a moment. If you've had enough time to at least give yourself a general sketch. If it's not beautiful, it's fine, okay? So before I move on, quickly answer 1, 2, and 3. Talk to your neighbor first. I just told you that. Just said that. All right, so everybody now look at the Bohr model on the blue sheet, blue reference table I just passed back. It's kind of small, that's on the back side, okay? So, question 3 here, you would not be able to determine without some diagram, right? You can't determine the wavelength simply from knowing it's dropping from n equals 4 to n equals 2. What you need to do is look at this. So, look really closely with your partner next to you. Look and see where the line that goes from 4 to 2 correlates with on the wavelength. So look for the line from 4 to 2 and tell me what wavelength correlates. Corbin?
46 nanometers.
46 nanometers? Or 486 nanometers, already said, okay. So, if we're looking, can't see those numbers now, can we? Alright, so 4 is this kind of middle ring area. You see it correlate down. So is this the line that we're looking at? No, because that drops to 1, right? So you keep going. Is this the line we're looking at? Yes. So it's going from 4 through 3 to 2. And that is going to connect to a wavelength given to you on your sheet. That's all you do is you read it. Now it's 486 nanometers, right? So you could therefore calculate frequency and energy from that. But I want you to see, it says visible, right? Right, so notice that these are in what unit here? Nanometers. As you look down on your sheet, you see the whole entire electromagnetic spectrum, but it's recorded in what unit now? Meters, right? It's up there right underneath the electromagnetic spectrum. What color would 46 nanometers be in visible light? Say again? Bluish, right? So 486 is not listed here because it's in meters. So it's like 4.86 times 10 to the negative 7th, which is falling between the two blue, in that blue area. But, you know, we're seeing that the maximum, or the smallest wavelength is violet, which is over here at the 400 nanometer mark, 4 times 10 to the negative 7, and then red is at the 700 nanometer mark, or 7 times 10 to the negative 7. So you can see that you can correlate the colors really easily if you know what you're looking for down here. We good? So if I give you a tool, just know how to use your tool. Okay, so hold on to that for a minute. You can check your problems under the problem set 5 that you maybe printed for yourself. I think some of my answers were jumbled up when I was making columns, so I actually uploaded the real answer document right under Unit 2. It actually pulls this up as just a Word file. So notice 1, 2, 6, 7, 10. You can do a quick check. This is the chart. You know the chart that's on the last page? The V means the frequency column. little upside down thing means the wavelength column, okay? And then up, I didn't put the energy on here because you guys can correlate those. So I'll make sure to know that you can find this on the website too, because I know some of you guys need to put some extra help there. Okay, you guys have 2 minutes. Follow instructions on the board.
Okay, so we're making a people atom.
All right, so Moon has planned to be the coordinator. Let's coordinate. Let's go.
All right, everybody up. Let's make a people atom. Okay, so since we're making a people atom of oxygen, we're gonna what are we gonna do? Somebody please tell me what we're gonna do. How do we make a people atom of oxygen? Does anybody know how to do it? Ryan, how do we do this? How are we gonna attempt this? Yeah, so we put how many people in the middle? 8 people in the middle. So somebody.
We have 8 electrons, 8 protons, and
All
5
right.
neutrons, protons, and then people surrounding us.
All right, so 8 people. Give them 8, 16, 22. Was that right? 22. Was that right? 24. Same thing. All right, 24 people in the middle, right?
Why did 16 people be in the middle? Other people
16.
Oh, 6. I didn't know what to put. Okay, no, it's fine.
Countdown.
All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Did I count y'all right?
Clump, you are dense nucleus.
Get together.
Clump.
All right, we're together. Yeah. That's 16, right? We got some extra. We need 2 more people.
No, we need one more. We need one more.
Yeah, 2 more. One more? All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
And it says come up with some hand signals for all subatomic particles. P or PG, please. So let's go.
All right, so positive, and then negative.
Okay, so
So I saw a hotline.
Yeah, we have 16.
no, we need to divide it.
Positive, boy.
Yeah, we just gotta make it equal.
Negative.
Yeah, so neutrons and protons have different signals, right? Okay, so 8.
All right,
This is the hand signal I'm thinking for negative.
yeah.
All right, neutrons. What are you? Neutrons. Okay. All right, so
Half and half.
I'm gonna take over just thinking about what I'm seeing. Okay, so in the nucleus, raise your hand if you are a proton. There should be 8 of you. Okay, that is the atomic number, also proton number, right? Raise your hand if you're not a proton in the nucleus. Okay, what are you? How in the world why are there 8 of you in there? Why are there 8 of you?
You told me to get 16.
I'm asking you. Why are there 8 in there?
Because there's 8 protons.
Why?
There's 8 protons.
Because that's the number.
Okay, so protons is a defined number. Like, you can't change a proton. It is the identity. It manifests. But atomic mass of oxygen is 15.999. But we know we can't have partial anything. So we rounded to 16. Hence, that's why we have 8 neutrons. It's not because it's matching. I'm sorry, 8 neutrons, not because it doesn't matching protons. All right, raise your hand if you're an electron. Way too many electrons. I need some people to sit down or drop out. Not at school, just a activity, please.
Hey.
Sit down. Okay, so electrons, you're gonna just like mostly. Okay, not everybody. Stand back up. We're gonna do this again. All right. So, Grace, let's go in order. Count off for me. Beautiful. If you did not count, sit down. Sorry, Andrew. All right. So I want my electrons to go in the way that they should be arranged around the nucleus. You guys should know this. How should they be arranged on the nucleus? Come on, people. Okay, sit back down. You're not helping yourselves out. Sit down. Everybody sit down. Thank you for your coordination efforts. Okay, so in effort to show you that we know like general electron configuration, because what does configuration mean? What does that word mean? Say again? Like how it's arranged. So we know the general arrangement of the atom. We know the protons are in the middle, the nucleus, within the nucleus, and then also those neutrons are there. And we know that electrons are around the nucleus, right? But how are the electrons around the nucleus? Are they willy-nilly? Are they in a certain structure? 6 So a lot of us probably know from like maybe biology or middle school, there's like 2 electrons first level, and then 8 the next level, and then 18 the next level. Who's ever heard that in their life? Yeah. So if you've ever heard that, then it's what they were trying to tell you up front is that, you know, there's a certain number of electrons can fit in this first energy level, a certain that can fit in this energy level, and then so forth. Now, of course, if I only have 8 electrons, I'm not going up to the 18 mark because I don't have that, right? So I'd only fill up what I needed. So there is a specific electron arrangement. That's what we're specifically learning today, but we have to kind of get there first. So you already have a good background. It's just now we're going to put like some more, you know, gusto to it, okay? So pull out your note sheet that I provided for you. It's got like quantum mechanical or something on it. Same sheet as yesterday from memory. So it's on the same sheet you're working on yesterday. And it's the lower left-hand side. We just haven't made it that far yet. All right, so we all know the Bohr model. We know that's on the blue sheet, the reference table. Did anybody look at the title of that? It says the Bohr model of hydrogen, right? So we now know that Bohr was only correct for one element, which is hydrogen. The Bohr model is actually not 100% true for every other element. So guess what? We got to come up with another theory. We have to expand our thoughts and think about what in the world are the rest of these elements doing, what do they look like, how do the electrons behave, and so forth. So Bohr termed his little rings orbits. Okay, orbits. And were they willy-nilly or were they a set structure? Set structure was like energy level 1, energy level 2. It was like little circles around the nucleus in their orbit kind of shape. But that only applies to hydrogen. So Schrödinger, who's the kind of the most modern scientist that helped with the development of the atomic theory, came up with the quantum mechanical model. Does that sound simple?
Yeah.
No, a quantum mechanical model? That sounds like it's going to be kind of like quantum entanglement and talking about alternate universes. Like there's a lot that goes into this. So if you're a Fringe, you guys, anybody watch Fringe? Fringe, not Friends? Never mind. Okay, you guys past your time. Okay. So this is stuff I have provided for you because it's a lot to think about and write. So write down what you need to on top of the notes that I provided. But I'm basically walking you through the next 50 years of the atomic history. Okay. So basically, the quantum mechanical model takes into account what's happening with electrons, where they exist, and what they're doing. So it doesn't, we have to kind of think differently about the electrons now. So Schrödinger and his crew said the same thing that Bohr did. Electrons are quantized. What's quantized mean again? Have a set amount of energy, right? So Bohr said the set energy was just based on how far it was from the nucleus. Really similar story. Like they both agree, electrons have a set amount of energy. So Bohr said it has a set orbit, right? Ring, 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 ring. But quantum mechanical model said that it does not have a specific orbit. It does not have a specific path. So now we're getting kind of willy-nilly. But there is going to start to be some structure here soon. So the Schrödinger and crew said that electrons can move around the nucleus freely. So some are closer and some are farther, but there's not a set path. And then after that, the orbital. Okay, so what did he do to the word that Bohr established? Added an AL, right? He's like, no, we're not going to call them orbitals. I mean, orbits. We're going to call them orbitals, which, you know, we could have come up with something different, but we call them orbitals now, okay? So the orbital, or the location in which we think the electron exists, is now the new term, and it's just basically telling you how probable is it that the electron exists in that area. So orbital is one way of phrasing that. Electron cloud is another way of phrasing that. When you think of a cloud, do you think that inside the cloud things are stuck where they are, or they can freely move within the cloud? Freely move, right? So they're not constricted in any way. So that's how that quantum mechanical model specifically differs from the Bohr model. So we made some advancements, and this is true for every single element now. So that's why it's talking a little bit more in depth about how this is applicable to the rest of the elements. So I'll show you the Schrödinger video shortly. So the quantum mechanical model, to get really specific, it comes up with 4 questions. Okay. So they came up with 4 numbers to describe where an electron exists in an atom. So think of it like this. Your address, right? Think of your address. Okay, or when you think about Coxon. We're in the overall globe, right? We're in the U.S. We're narrowing down, right? We're in North Carolina. Okay, get more specific. We're in Concord. Get more specific. Okay, Cabarrus County. Oh, Cabarrus County is probably been Concord, right? And then Coxville Road. Keep going. Say again. Coxville High School off of Coxville Road. And where are we at now? 1627, right? So you can basically assign 15 different numbers from a big, grand, dispersed location, and you can narrow that down to a very, very specific location if you have the opportunity to assign each of those like a number. So an atom works the same way. If we're like, hey, it's in this energy level, okay? But it's on this side of the energy level, and it's in this area of that side, and then it's spinning this way. We can get really specific about what specific electron we're referring to, and that's what these are supposed to do. So they're a little complex, but here we go, okay? So, N, we've seen this before, right? N, where do we see it? In the energy level, so we all should know that N represents the energy level that we're describing. So if the electron is in N equals 6, is it close or far, or close to the nucleus or far away? Far away, right? So if we're in N equals 1, we are close to the nucleus. So it basically just says, where is it at with relationship to the nucleus? And that gives us a size comparison. So would N equals 6 or N equals 1 be a bigger orbital? 6, right? Because 1's here, pretty teeny tiny, and 6 is going to be probably way out here, much, much bigger. So that gives us just a size comparison. Then we go down to the L number, angular momentum quantum number, just remember L. And it doesn't give us information really about the size anymore. It gives us information about the shape of the orbital. Well, now what shape did I draw here? A circle. So I drew, now this is 2D because I'm not really great at drawing 3D on the board here. But what do you think this would look like in a 3D shape? A sphere, okay? So we give each of these orbitals shapes a different letter to describe them. S, P, D, F. Where'd you see that? Already, you've already seen it today. On that period table you drew, okay? So this is going to start to ring a bell, okay? So S, and this is what you need to know. S is spherical, okay? S is a spherical shape. P, I'm going to draw these over here, is a dumbbell shape. Like a dumbbell, like a weightlifting dumbbell, okay? D is a double dumbbell laid over top of each other.
Please allow part interruption. Would you send me there to the office and you will return?
Shortly, thank you.
Thank you.
Hold up, thank you. All right, so S is a spherical shape, P is a dumbbell, D is a double dumbbell laid on top of each other, and F is a flower. It's like 1, 2, 3, 4 dumbbells laid on top of each other. It doesn't have to be that pretty, okay? So essentially, as you get from S, P, D, F, the orbitals get kind of more elongated and dispersed. They change their shapes. So you can have a little bitty sphere in N equals 1, or you can have a huge sphere in N equals 6. You can have a little bitty dumbbell in N equals 2, and a really big dumbbell in N equals 6. So it does change size with the shape. So after we determine the shape, we determine which orientation that shape is in. Because think of a 3D shape, right? Well, how many axes can you think of in a 3D shape? 3. X, Y, and Z. So a sphere, how many different orientations can a sphere take on? 1, right? You can't change the orientation of a sphere. So you have, sorry, it says it right there, guys. Okay. So you have a 1 singular orientation that a sphere can take on. So in S, there's only 1 orbital. That's your sphere right there. There's 1 orbital in the S-shaped orbitals. But how many different directions can you throw this dumbbell? This is the what direction, or axes? Y. This is the X, and this is the Z. So it can take on how many different orientations? 3. There's the, I'm going to say P, Y. Here's the PX, and then the Z one kind of comes out of the board and then goes into the board, like that. Okay, so I'm going to stop drawing these from now on because they get really complex. So basically what you know so far is the S orbital, there's only 1 version of it. For the P orbitals, how many versions? 3. So 3p orbitals. And then it's going to go up by 2 each time. So guess how many d orbitals, orbital orientations can it take on? 5. Okay, so d will have 5 orbitals, and f will have 7 orbitals. All right, so 1, 3, 5, 7. 1, 3, 5, 7. All right, so we went from size to which shape we're referring to the orbital is taking on, to which orientation that shape we're referring to is actually in. And then now we've gotten down to Cox Middle High School. Now we're looking at like one individual student in that class or in that school. So that's what this last piece is. It's like looking at one singular electron in that orbital. And basically all we know about electrons is that one of them spins clockwise in the orbital, the other one spins counterclockwise. And that's all we have to know, okay? So clockwise or counterclockwise. And I moved this by accident. 4, the spin of the electron. Okay, so the first one was energy level. We basically know exactly kind of how far away the electron is from the nucleus, and we got all the way down to which electron is it and how is it spinning. That's all we're doing is figuring out where electrons are. Why do we care? Right now you don't care at all. But we care because as soon as we start to figure out what electrons are doing, we figure out how reactive they are, and as soon as we know how reactive things are, we know what we can do with that species. So like what's something that's really not reactive at all? Argon, right? It's in our air. Doesn't do anything to us. It doesn't do anything for us. But it's inert, meaning it doesn't react. And that's because its electron configurations, where the electrons are, is super, super stable. Doesn't want to react. But what's something that is really reactive? Sodium. Who's ever seen sodium like in water? Maybe you've heard about it. Sodium in water is like super duper fiery explosive. Okay? It does not play nicely with water. And it's because its electron configuration is not in a stable place. And so the electrons react, and it does it like some fire damage. So that's what we're talking about more today. Okay, those are your pretty pictures. There's your sphere. There's your p orbitals. That's them laid just on top of each other. There's your d orbitals. There's 5 of them. And then how many down here in f? 7. 1, 3, 5, 7. Right there we go. They're like donut shapes. Like I've said, I don't want to draw this because they get pretty complex. Okay. This part I'm going to scooch past because we just looked at pictures. And now you know your 4. This is just really simplified. Where it is, based on the nucleus, the second kind of narrowing down the electron is the shape, and then which orientation of the orbital, and then is the electron moving clockwise or counterclockwise. So we just talked about that. Okay, who's ever seen something like this before? Okay, this is what you're used to. Do not draw these in the class because now 7th grade they lie to you just to get you through. They do, because your brains would explode if you had to learn quantum mechanical theory in 7th grade. But they have you do this because you know electrons are arranged a certain way. But now we're actually going to learn the truth of it, which is what these look like. But we're not going to draw them over and over again. We're going to have a code, a secret code we describe to tell us how the electrons are arranged. Okay? These should look familiar. Write these down. I would start someplace on some clean paper now because you're probably going to have to clean your stuff. And how about that periodic table you sketched earlier? Hey, electrons are arranged in a very, very specific way around the nucleus. That's the big idea. But you can't just be specifically arranged around the nucleus if there's not rules into how you are arranged in the nucleus. And these are the rules that describe or govern how electrons are configured. Do you remember these from reading Code 5? Vocab terms, basically. So just memorizing definitions and not applying them is useless. So we're getting ready to apply these terms, but I like to think of things as simply as I can because I have to remember them, right? Like it's probably difficult to memorize these as they are because we've simplified them, but they still they don't have a ring to them, right? So I like to make up maybe memorization tools or acronyms or things like that. So here's how I've remembered it since 10th grade. Off-Ball's principle starts off awfully low. And so essentially that means as an electron is put into an atom, it's starting off in the lowest energy level. Off-Ball, awfully low. Off-Ball, awfully low. I can remember that. So you're putting an electron in n equals 1, then n equals 2, and so on, because you're not going to throw it in n equals 6 if you don't need to. After that, you're going to have to decide on how many electrons can you put into each orbital of the atom. Well, you can't throw 15 in there because the orbitals are not very big. Plus, what does one electron do with another electron? They don't react. A negative and a negative. They repel, right? They're going to be super repulsive to each other. They don't want to be near each other. We can't put more than 2 electrons per orbital just because of the nature of how electrons interact with other electrons. So I always think poly pair. Oops. Poly pair. I can pair up electrons, but that's as far as I can go. Okay, 2 electrons per orbital. And then if I have an orbital, and I have an electron here and I have an electron here, we know that they potentially could repel. So if I don't have to put 2 electrons in an orbital, I won't. Because like I said, they repel, right? So my rule is if I don't have to put 2 in, I'm not. Therefore, I call that Hund's-One's rule. Hund's-One's rule. Meaning I can put 1 electron per orbital or suborbital, sublevel until I have to actually count. I'm like, if I need this space, I need this space. I put an extra electron in there. So alpha, awfully low, poly pair them up, Hund's-One's rule. That's how I remember these. Got it? At least in terms of memorization. Now we're going to apply this. Okay, so let's start with, okay. So we're going to use these rules to write out a code. And the code, the secret code, is just called an electron configuration. Instead of drawing them every time, we use numbers and letters to describe where these electrons are. This is an example of what that looks like. These are other examples of what that looks like. So what I want you to know is how to read the code. The first big number, this is what you should be writing down. I should not have to prompt you to write this down unless you're just a good listener and you remember everything you ever hear, okay? So the big number is the energy level, aka the N number. The letter next to it, now we've seen S 3 times today just alone. S is describing how the orbital is shaped. What are the options for this one? What letters can go here? S, P, D, or F. What numbers can go here? 1, probably 1 through, how many energy, sorry, there's only 7. There's usually a maximum of 7 energy levels, and I'll tell you why in a second. And then we know that orbitals, each individual orbital can only hold 2 electrons, but you can have between 1 orbital and 7 orbitals per sublevel. Some of them only have 1, others have 7. We'll talk about this in a second. So, because you have to describe how many total electrons are in this orbital or in this sublevel, you put the exponent up here to represent that. Yeah. 1 orbital between 1 orbital and 7 orbitals. We'll make sense of this more in a second, okay? So what I'm showing you down here are just more examples of how an electron configuration looks. So this is saying there are 6 electrons in the p orbitals. This one's saying there's 10 electrons in the d orbitals. This one's saying there's 2 electrons in the s orbital. So that's how you read these. But we're actually going to build our own atom from scratch here with electrons, okay? So let's look at hydrogen, right? Everybody can see hydrogen. It's the first element of the periodic table. How many electrons does it have? 1, right? So the way, actually, I got to go back to warm up, okay? Oh, I probably had a periodic table just nearby, but here we go. Okay, the way this works is knowing that your helium actually belongs right here. You have a little extra box there, so I'm just getting rid of it over here. So what we do is we read the periodic table across, and every single time we go into an extra element, the next element to the next element, we're adding an electron. Because what is this, like, for example, what does atomic number 1 mean? It means there's one what? One proton, really, but we know that it's a neutral atom. Protons equals electrons, right? So as we go across the periodic table and we see the atomic number, we're actually seeing the electron number as well, assuming it's neutral. So if I have one electron, that's all I have. I'm going to put it in the first energy level, in S block, or S orbitals, because it's the simplest of them all, and I'm only going to have one of them. So the electron configuration for hydrogen is 1s1. So you'll notice that I've numbered these 1 through 7 because the energy levels actually correlate with the periods on the periodic table. So if you have a periodic table in front of you, it has all the answers on it. You just have to follow the rules. So let's say I want to go to helium. Helium I've just artificially placed right here, correct? So how many electrons does helium have? 2. So hydrogen was 1s1. Helium would be 1s2 because there's 2 electrons. And you can count them, 1, 2, as I go across the periodic table. As I count each atom or element, it's counting extra electrons as I go. Okay, but now I'm looking at lithium. Where's lithium at here? It's at the 2s level, right? Okay. So lithium, which is right here, I have to start by building always from scratch. So I can't just go straight to the 2s because the 2 means second energy level. I can't go straight to the second energy level. I build from the inside out. So I have to start building as first energy level, 1. I go through all of the little s orbital, so that's 1s, 2, 1, 2, so that's all I got through s. So far I've got 2 electrons, and they're just in the central, in the S-shaped orbital. And I can go all the way across this periodic table. There's nothing else here, right? The p's are actually below this, and this s has been removed, so I've got nothing else to apply. I'm going to keep reading it like a book. Now I'm on lithium, right? But now I'm on the second period, which is the second energy level. So I've got a 2. But now I'm just in that bigger s orbital. I'm just in a bigger sphere. So I'm still in s. But how many electrons in? 1, right? So I'm on the first group still, so this is 1 electrons. So the electron configuration for lithium is 1s2, 2s1. So what you're doing is you're just adding electrons every single time you build a bigger and bigger and bigger and bigger atom because they have more electrons. The way you can check yourself is saying, okay, go back. Hydrogen has how many electrons? 1. And there's 1, I've denoted via the exponent right there. How many electrons does helium have? 2, because it's the second element. 2. How many electrons does lithium have? 3. 1, 2, 3. The exponents are identifying the number of electrons. So they should sum to the number of electrons. Right, I'm going to keep doing more examples until it clicks. It's going to take a minute, okay? So let's say I want to do chlorine, okay? So you have your periodic table now, right? I'm going to scooch back to where we were. Okay, here we go. Chlorine. Now, yours is colored and got some crazy stuff on it, SPDF. But chlorine is way over here, right? So you'll notice that it's going to have total how many electrons in the end? 17. Right? So I'm literally following the periodic table as I read across, and if it says S, I write an S. If it says P, I write a P. If it says D or F, I write a D or an F. So I have to go from here through helium. Remember, helium is not there. Okay, so as I run through these 2, how am I arranging the electrons there? 1 s orbital, and how many are there that I pass through? 2. So far I've built a little bitty sphere with 2 electrons in it. And now I'm going to the next bigger sphere because I've exhausted the first row of the periodic table. Now I'm on the second row of the periodic table. So now I'm going through here. Bigger sphere, what is it? 2. The sphere is S, right? And I've got 2 electrons in that new orbital. So that's 1s2, 2s2. I've gotten up to 4 electrons. I got 17. All right, so I skip, but hey, I'm still in the second period, right? Because I haven't moved levels, so it means I'm still in the second orbital. But now I have to go through all of these. So 2. So now I'm in p orbitals. Those are the big lobe-like ones, right? The D or the dumbbells. So 2p, but how many electrons are here? 6. Now let's, before I move on, let's make sense of this. What were the shapes of those p orbitals? Dumbbells. How many of them were there? How many dumbbells in the p? So there was p that could go this way, which was p on the x-axis. There was one that goes this way, which is on the p y-axis and z-axis, right? How many electrons can go in one orbital? 2. Definition, right? Pauli's rule says 2 electrons per orbital. 1, 2, 3, 4. Right, so that's 2, that's 2. 2, 2. How many is that?
6.
Why do you think it's 6 over there? Because what? We have in the p, all the p shapes of the p orbitals we have, this is it. We got 6 electrons. It doesn't matter how big the p, like if it's the second level, the third, or the 7th. There's a total of 6 electrons that can be totally filled in the p orbital systems. Okay, so that's why it's always going to be 6 as you count across there. Okay, so now we have 2p6 handled. Moving on. Now we're in the third energy level, so we're kind of big. We're getting bigger, but we're in the spherical shaped one, the S. But how many electrons fit there? 2. Okay, so total electrons so far? 12. Now we're going back to the p, but where do I stop? So how many electrons? 5, right? So 3p5. Because at maximum, I can put 6 electrons in there, but if I don't have the total, then I don't put the total. I put as many as I need to, which is 5 here. So before I move on, count the exponents. Add them up. 2, 4, 10.
12,
Hallelujah. All right, we got it. That's how you can check yourself at the end. Okay, so basically you build the electrons from the inner core to the outside. Okay, I want you to do this for, I have to tell you one rule. I actually tell you 2 rules. So D block, which is this transition metal area, right? If you get into D block, once you cross this barrier right here, you take the N, what's N? Energy level, aka period number. Okay, so this is 1, 2, 3, 4, 5, 6, 7. You take the period number and you subtract 1. When you're in F block down here, once you hit this part, which fits in to the periodic table, like right there, you see 57, 58, 89, and 90. They fit in there. F block, you do N minus 2. This will make sense when we do it, okay? So I want you to write the electron configuration for cobalt. Start at the top. Use cobalt. And of course, a real periodic table would be helpful because your little sketch was just to help you identify big pieces. A real periodic table you can count a little bit easier. You just got back in here talking to you for a second. That's why I think it's What do you want to write at what do you want to write right here? But what number? So like you're in the
So it's 2.
You're in 4, aren't you?
Well, I'm reading this thing, says 3.
Well, it was a sketch. Like, use a real periodic table so you can count, because it's easier to count with the actual squares. Maybe you drew it wrong on that. That's a possibility. But go from here. You want to put 4. Like, did you do 4 as 2 already?
Yeah, for those.
Okay. And then you want to put 4, but you don't. You put. Oh, good, good. Okay. So yeah, you put 3. All right, and come back to me. Let's get started. All right. So we're just gonna chant this, okay? So get me through here. 1 S 2. Okay, done with the first row.
2B6.
And we got to neon, okay?
3S2. 3B6. 4S2.
And so that if we stopped here, this would be the electron configuration for who? Calcium, because we build up all the electrons it takes to make a calcium atom. But now we're going inside to D block, so what do? So 4s2 and then 3d. Yay, 7. Okay, so that at that point we would be in D block, right? But we're gonna keep going. Let's go over to bromine. I'm not erasing this, okay? So get me to the end of D block. I'm just gonna modify this because this right here currently is representing cobalt, right? So let's modify that. So 3d10 gets me to the end of D block. You do have to stop at the end of a block. That's what we kind of blocked them off at the beginning of class. So 3d10 gets me to stop at zinc, yeah? Now get me to bromine.
4.
Good. It's only D block we use the subtraction of 1. So we go back to the original counting method, which was the 4th energy levels here. And that's 4p5. All right. How many electrons should be here? 35. 10, 10, 10, 5. Yep, 35. There it is. Okay, so basically what you're looking at is how to build an atom, but our coding system just makes it easier versus drawing like bazillion orbitals. Let's look at some correlations though. So how many orbitals were available in S block? 1. Orbital 1. It was a sphere, right? You couldn't change the sphere in any other direction. It was a sphere. So how many electrons fit in that sphere? 2. 2 all the way down here in S block, right? How many different orbitals do we have in P block? 3 orbitals, but a total of how many electrons? 6. We have a drawing right here. That's why you have 6 electrons across in P block. How many orbitals do you have in D block? 10. Say again? How many orbitals were there in? Okay, so there were 5 orbitals. Remember, I went 1, 3, 5, 7. So 5 orbitals, but the total of how many electrons? 10, which is why there's 10 here. Okay? In F block, how many orbitals? 7 orbitals, but a total of how many electrons? 14, so there should be 14 across here. Okay? Now, sometimes it's modified because it's based on the periodic table you're looking at. Sometimes they take out lanthanum and actinium, they put them down here. Sometimes they leave it like this. I like this periodic table the best, but we're going to work with what we're working with, okay? All right, so we've drawn this, or we've described the electrons, and now we're going to draw them in a really simplistic manner. We will not be drawing these babies, okay? So let's do it as simple as can. I'm going to go back to chlorine, okay? Chlorine. And what was your electron configuration for chlorine? 1s2, 2s2, 3s2. That's it, right? Okay, so when we draw an orbital now, we're making it simple. Okay, you need to probably write down chlorine's electron configuration, or maybe draw an arrow so that you know that this is connected. So this is an electron configuration. But if instead I ask for a orbital diagram, you must actually draw a diagram. You must draw pictures, because the configuration is just a bunch of numbers. The picture is going to show me what the electrons are doing. So you have 1s, you draw a line, you label it 1s. How many electrons are in there? 2. You draw one spinning up and one spinning down, which is supposed to correlate to the spinning clockwise and counterclockwise. Okay, how do I draw the second orbital? You put a line, you label it 2s. How many electrons are there? 2, 1 up, 1 down. Okay, 2p6. Here's where we have to just get a little bit more detailed. If I draw 3 orbitals, I don't know if they're supposed to be like collectively together or not. So put like a little bracket, call them all 2p because they're all representing 2p. It's just one that's in the x-axis, the y-axis, and the z-axis, but we don't need to get that detail. Just put the whole shebang as 2p. And then when you're filling these electrons, what are the rules? We had off ball. Well, we've been doing that. Off ball, awfully low. 1, 2. Okay. Who was next? Poly pair them up only if you have to, because what does Hun say? Hun's 1's rule, right? So let's fill them appropriately. We put 1 in the orbital, and we put 1 in the orbital, and we put 1 in the orbital. But we're like, oh darn, I got to put all 6 in there, right? So I'm gonna put second, 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 and this is my lazy arrow, but it's an arrow. Okay. So there's total. How many here? 6, as you were supposed to do. 6 according to the electron configuration. So tell me how to do the last 2. Line, 3s, up and down. Okay, so that's 3s2 done.
Line, 3p.
Hold on, how many lines?
Oh, 3 lines.
3 lines, because there's 3 orbitals in p block. Okay.
Bracket. 3p. Oh.
And how do I appropriately fill this? One each first, so that gets me to 3.
And then down.
And then we're done. Because I hit 5 already. So I've got 5 here. So on this one, I wouldn't know if you filled it right or wrong. I wouldn't know because you're going all the way up and leaving 1 empty, right? But what I would know is if this was a 3, right? I'm just going to draw it down here as if it were 3p3. So if it were 3p3 and you did boom, 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 you'd be right. But what most people do, because they forget about the Hun's 1's rule, is they do, so that's 3p, they go 1, 2, 3, I'm done, but that wouldn't be right because you wouldn't be following his rule. Hun's rule, okay? So that's wrong. So that's why I want you to keep thinking about those rules as we go. Okay, so that's an electron configuration, that's an orbital diagram. So let's talk about just a little bit more that we can figure out now from these orbital diagrams. First off, how many unpaired electrons are in chlorine? 1 unpaired electron, because all the rest of these are paired. All right, who's ever heard of valence electrons? You're in Miss Austin's biology class. I know for sure you did. Valence. Let me write that word up here. All right, so you should be writing this down. And if you do not know what a valence electron is, and if you don't, it's okay. I'm going to show you right now, okay? So a valence electron are the very outside electrons in an energy or in an atom. That's the simplest definition I can give you. Very outside. So if I want to put that in more technical terms, it means the last energy level. So, last energy level. Who's the last energy level for chlorine? Loud and proud. 3. Okay, not 3p, not 3s. Energy levels are represented by what? Just a number or a period, right? So the number 3 for this one, n equals 3, is the last energy level we see for chlorine, right? So how many electrons are in the 3rd energy level? 7. How do you know? Sorry, guys. Apparently I don't put my phone on silent. Say again. Muy bien. Okay, so that's it. You just add them up. So 3rd energy level, 3s. There's 2 sections of those because they're shaped differently. It's s orbitals versus p orbitals. And there's 2 plus 5, which gives us 7 valence electrons. 7 VE. Sorry, 7 VE means 7 valence electrons. So that's it, how one you can count from an orbital diagram. If you're looking instead, not an orbital diagram, but an electron configuration, it's pretty clear too. You see the 3s2 and then the 3p5? It's the same story. These are your valence electrons. And somebody tell me what group chlorine's in. What group is it in? seventh group. Does this make sense? So the halogens, right? But it's a 7A, group 7A. So you see 7 on the periodic table. You can see the 7 from the electron configurations, and you can count the 7 in the orbital diagram. So it's quick to figure out the valence electrons if you have all these options. Okay. Let me give you a couple more questions to practice with. Okay, I want you to do lead. Let's go down to lead. I want you to write the electron configuration. Process of the person next to you. It's around 80. These are the ones that I just provided with you today. All right, guys, so a couple of you guys have already seen the magical part here when you get to F block. So most of you guys probably very quickly made it through 4P. You went to 5S. Once you hit 5S, you hit D block again. So what did we do here first? When we got to D block, you subtract 1, so it's not 5D, it's 4D. And then we go back to 5P6, 6S2. Where are we on the periodic table? Who is 6S2? Barium, right? Barium. So the weird part is depending on the periodic table you're looking at, it could just slightly vary where it inputs F block. But if you look on the periodic table on the wall, do you see lanthanum and actinium are highlighted in different colors right there? It's starting to show you that before you hit D block, you must do F. You must do F block. So I want you to insert the first row of F block, which is 14 in total atoms or total electrons, before you proceed to D block, before you proceed to P block. So there should be 14 across regardless of the periodic table you're looking at. So 4F14 goes next. Remember when you hit F block, it was -2. So we want to put a 6, but we don't. We put a 4. You with me? And then 4F14. Then you get out of F block and you go back. So I did all the little light Carolina blue ones, and I go back up here, and I should do all 10 of D block, but that's now 5D because D only subtract 1. And then I finally leave D block, and I go boom, boom, 2 over into P block, and you have 6P2. Total electrons here should be what? 82. And if you counted them, you would see there are 82. How many valence electrons supposedly does lead have? 4. It's weird because there's 2 here, S2, or 6S2, and there's 2 here, 6P2. We'll find out later that lead can actually change its electrons based on its valence electrons by 2 or 4. Alright, so that's the only example I'm going to do for F block. Alright? I'm not going to make you draw the orbital diagram for this. You're welcome. Okay? So why in the world are we like minusing 1 and minusing 2? It's because, and this is how my teacher taught me. I had no idea what electron configurations were when I left high school. I was like, what is this? And so I started teaching. I was like, oh, okay. So they made me memorize this guy, which is the off-ball diagram, to memorize the order in which you should fill electrons. 1s, 2s, 2p, 3s, 3p, 4s. What's next? 3d. So I had to memorize that, but I told you the trick. If you have a periodic table in front of you and you know the tricks, you can do it without memorization. You have a tool now. You should know how to use your tool. It's with you at all times. So it's simply because 3d is slightly lower energy than 4p. And then as you keep going up, it gets really crammed together, but it's 5s, 4d, 5p, 6s, 4f, 5d, 6p. That's actually what we just did. Just they're so cramped in energy. That's why, like, mostly you just follow the periodic table, but you can definitely see why now we use the periodic table because you would have a very hard time memorizing this. But another thing to note here is how's the energy differences between energy level 1 and energy level 2? Pretty large. It's a big energy gap. But then between energy levels 4 and 5, not so big. 6 and 7, even smaller. So we should definitely notice that there's a bigger energy gap in the lower energy levels and a smaller energy gap in the higher energy levels. Okay, that's one thing to note from Paul's diagram. Okay, so we're going to work on this for a couple of minutes, and I have a video for you. This is the first part of problem set 5. Hopefully you skipped that last night and didn't even attempt it because you didn't know what you're doing. But I want to leave this here for you to attempt the ones you feel comfortable doing right now. I'll answer some questions in about 10 minutes, okay? So if it were me, I would start with 3 and 4 because those look exactly like what we've been doing right now, okay? I would start with 3 and 4 and then back up to the others. So I think the little blue one, the reference table provides you, would be a good point to start using because this is what you get like on a testing situation. You would use your big old colorful one. The only distraction here is there's a big old gap in the middle. You see it? Obviously, there's not a gap in the middle of the table. So if you want to start looking at this, this is what I would use for that. So that you can follow through. It's just the best option.
It was originally 8 pages, and I made it into 1. An 8-page reference sheet is not the reference.
Andrew did a good job explaining it. I just don't understand.
All right, we need to get this started. We'll start on one. So later on. You want to start on?
Let's start all the way through the third grade. That's why that way it says 2 I draw two uppercase triangles. And then draw
So just heads up real fast, I do want to make sure you're not getting yourself in trouble right now. Sulfur, which is 3B, who's already attempted it? Okay, 1s2, 2s2, blah, blah, blah. You have your electron configuration because you can read that off the periodic table quite easily. It stops at 2p4. But when you're drawing this this orbital diagram, how do you draw this last one? Like, how do you draw the 3p4 area? You have to draw 3 lines. I don't care if you use all the orbitals or not. If you're in the p sublevel, that sublevel contains 3 orbitals. It doesn't matter if they're empty. You have to draw all 3. You label it 3p, but then how do you fill this up? 1, 1, 1, and then a doubled up one. Okay, so that's you following Hund's 1's rule and the fact of the matter of there's 3 orbitals. So just make sure that you're not off par here. Basically, I can ask you now. Unfilled, not too far. There's one total. 3
That's the 82. So it's not right here. Yeah.
Looking good. Good. One immune. Very good. Alright, finish the one you're working on. I'm going to demonstrate one from 7 because you actually probably can figure it out, but I want to make sure you're clear before you go, okay? Because you know what these charges actually mean. All right, eyes back up here in 3, 2, 1. Let's look at 7. Pick your poison, A through D. C. Of course you guys should C. I was going to wait on that one because it's transitional, but I'm going to do it, okay? So let's write out the electron configuration for copper. Ready? Get me started. Electron configuration for just straight copper, not copper 2+, straight up copper. 1s2, 2s2. Okay, currently we are at what? Neon. We're at neon, okay? Keep going. Currently we're at calcium, okay? We're going to show announcements in a second. Okay, our calcium, and then I need to get a copper. Give me there. 3D9. Okay, so we have what? 29 electrons? 29 it is, okay. So, you'll notice it says 2+. What does that mean to you? 2 what? 2 less electrons, because you can't become more positive by gaining electrons, right? Electrons are negative. So you lost 2 electrons. Now, you have an atom, right? And it kind of builds itself like this. Do you think it's easy to grab some electrons from in here? It's like way inside close to the nucleus. Plus the nucleus is holding on tight. So which electrons would be the easiest to grab? The valence shell, right? So the valence electrons. Who are the valence electrons here? 4s2. Good, because 1, 2, 3, 4. 4 is the highest number I got to, highest energy level I got to. These are the 2 electrons, right? There's 2 of them. Those are the 2 that get swiped away. They get lost. So what you would probably do for most of these first is to write out the full electron configuration and then say, okay, where am I going to lose electrons or where could I shove some more electrons? Because like these negative ones, that like for oxygen, for example, what happened here? It gained 2 electrons. You can't just willy-nilly like, let me make a whole another electron energy level. You're going to put them where there's space. That's why those orbital diagrams, you're drawing them, you're seeing some extra spaces, right? Like carbon has 4 extra places, so and so forth. So for this one, I would rewrite copper, and I'd not write this section here, because it lost these 2 valence electrons, and then that would become copper 2+. Who's picking up what I'm putting down? Just give me a head shake or hand, okay. So it's all that backed up to the subatomic particles yet again, electrons, and then how does that make it look different? So I do want you to try number 7. So specifically, homework, problem set 5, you should have most.
okay? So you have a little bit more light stuff to practice, but you haven't done much of the chart, and then those questions 1 through 7 right there, okay? The definition items and the definitional things can kind of come in as we talk more. So I'm saying most of it, so that's about a good 70%, okay? The more you do now, the less you do later, the better you know it tomorrow, okay? All right, so I'm gonna leave that there for a second, and I'm gonna turn on announcements. Which one? On which number? I'm sorry. 7A. Write down the electron configuration for oxygen. Karen, what is it? Electron configuration for oxygen. 1s2. 2p4, right? That's oxygen, right? What does this 2 negative mean to you in terms of electrons? You add 2 electrons. Where do you think I can fit those in here? Okay, well, I'm going to draw it out here then. I'll let you see it. That's it, right? All right, so that is the orbital diagram, right? Yeah, so instead of being 2p4, I'm going to add 2 electrons. 1, 2, and then that wouldn't be 4, that would be. I think it might be easier to draw if you need to, but you can also just paint where it's going. Okay? All right, I think you guys did a good job, and I'm thinking I caught all of you guys up to speed on this, but if I didn't, text me, because I can quiz you on it, or you can just legitimately tell me. I'm like, I don't know what the